Okay, in this video I'm going to talk about the 9-point circle. So this is a circle, so in a triangle we draw the altitudes. So we take the feet of the altitudes and we take then the midpoints of every side. So these points. And we take the midpoints between the vertices of the triangle and the orthocenter. So the midpoints of these segments. So let me select these points in another color. Yeah. So again, so let's denote ABC. So the feet of the altitudes we denote by HB, HA, and HC. The midpoints of the sides we denote as MB, MA, and MC. So this is the midpoints. The midpoints means that like MB is equal to MBC, AMC is equal to MCB, and BMA is equal to MAC. Yeah, and then the midpoints of these segments basically. Yeah, and the theorem says that all these 9 points lie on a single circle. So yeah, so we need to denote the midpoints. So let's denote them. So let's denote this NA, NB, and NC. So the theorem says that the points HA, HB, HC, MA, MB, MC, and NA, NB, and NC lie on a single circle, which is called the 9 9-point circle. Yeah, so let's prove this, and there are also like it's also known where the center of this circle lies, what is the radius of this circle, like in terms of the other elements of the triangle. Like I think I will make a separate video about this. So first, just in this video I will prove only that these 9 points, yeah, by the way, notice that it's called 9-point circle and there are exactly 9 points here listed. So in this video I will prove only that these 9 points lie on a single circle. So the circle goes like this. Okay, so let's start with so we will start with the feet of the altitudes and we will add by 1 point there. So we start with, so I will draw again so that not to obscure the essence of what is going on, like I will draw only what is needed. So we have the altitudes for now only, and we take only one midpoint of one side. So let's say we take MB and the three feet of the altitude. So HB, HA, and HC. So everything else we don't draw on this picture. So yeah, so the goal now is to prove that, so we consider the circumcircle of the triangle HA and HB and HC. So so the circle that passes through these 3 points, and we are going to prove, so now the goal is to prove that MB, the midpoint of AC, the point MB also lies on this circle. So we take the circle of the triangle HA, HB, HC, and we will prove that MB lies on it. Okay, so then the other 2 midpoints would be just similarly by a similar argument. So basically we just need to calculate the angles. So when we draw this line, and this line. So now let's denote the angles of the triangle, of the original triangles alpha, beta, and gamma. And now we calculate the angles. So basically, to prove that these 4 points lie on a single circle, like one of the criterion of a cyclic quadrilateral is that the external angle for one of the vertices is equal to the opposite internal angle. So basically these 2 angles are equal to each other. So this is if and only if the quadrilateral is cyclic. So this is one of the criterion, and that's exactly what we are going to do. So we are going to prove that this angle is equal to this angle. So the angle HA, HB, C, I put the question mark, we haven't proved it yet, like we need to prove this, is allegedly equal to MB, this is not H but M, MB, HC, HA. Yeah, so this is what we are going to prove. So I will remove for now the designation that they are equal. We don't know that yet. So we will calculate the angles. So notice, because MB is a midpoint of the side AC, so we have this angle. So the angle ACHC, so this angle is calculated as 90 degrees minus alpha, right? Because in the right triangle AHCC, right? So one angle is alpha, another 90 degrees, and the third one is 90 minus alpha. So, and then we have the median in this triangle. Therefore, this median is it's a well-known property that the median in a right triangle from the right angle is equal to half of the hypotenuse. So it's equal to both of these halves, and then this HCMBC is a isosceles triangle, and this angle is equal to also 90 minus alpha. So the in the isosceles triangle, two angles must be equal. And then we calculate this angle. This angle is calculated as it is equal to this angle because the quadrilateral HCBHAH, so this is H, is cyclic, because the two opposite angles are 90 degrees, right? HC and HA, these two opposite angles are 90 degrees, so the sum of them is 180, so it's cyclic. Therefore, these two angles subtend the same arc HHA in the circumcircle of this quadrilateral, so these two angles are equal. So this angle is calculated as 90 degrees minus gamma from the right triangle BHBC, right? So therefore this angle is also the same, 90 degrees minus gamma. So now the angle that we need, so this angle MBHCHA, so this angle is calculated as the sum of these two angles that we just calculated. So it's equal to let me write it here. So this is equal to 90 degrees minus alpha plus 90 degrees minus gamma, right? And this can be simplified. So this is 180 degrees minus alpha minus gamma, but we now recall that alpha, beta, and gamma are the angles in the original triangle ABC, and so their sum is 180 degrees, so therefore 180 degrees minus alpha minus gamma, this is exactly the angle beta, right? So now the angle HAHBC, so this angle is actually equal to the angle so this angle is equal to beta because the quadrilateral ABHAHB, so this is because A, B, HA, and HB is cyclic. It's cyclic because the angles AHBB and AHAB are equal to each other. They're both 90 degrees. And so the Yeah, so they're both 90 degrees. So the external angle HA HBC at one vertex is equal to internal angle at the opposite angle, which is the angle B, which is just beta. So that's what we establish, and so we see that on the left hand side and on the right hand side we have the same thing. So basically this equality holds, and we can remove the question mark. So this equality holds, which proves, so because these two angles are equal, this proves, so from this it follows that that's what follows. I already wrote this, that MB lies on the circle. So the MB, so the midpoint of the side lies on the circumcircle of the orthic triangle. So of the triangle HAHBAC. So similarly, the other two endpoints, the other two midpoints, so A and C also lie on the circle. That's denoted by omega. So we take the circumcircle omega of this triangle, and now we proved that MB lies on omega, and similarly the other two midpoints, MA and MC, also lie on omega. So because of the symmetry, right? So now 6 points lie on this circle. Now we need to prove that the other 3 points lie on the same circle. So we consider the midpoint, so NB basically, the midpoint of BH. So the midpoint of BH is again, so in the triangle BHCH, so this is a right triangle, and HC and B is a median in this triangle, right? So these two segments are equal. So this is a median, and so we can calculate them. Okay, let's draw a separate picture. So yeah, so we have this midpoint and P. This is a median in a right triangle, so it's also equal to half of the hypotenuse, right? So we have A, B, C, H, B, H, A, HC. Yeah, so this is also equal because in the other right triangle BHAH, this is also a median, so it's also equal. So now we basically calculate this angle, and this angle, right? So okay, so in the triangle, so in the quadrilateral AHC HB, so in this quadrilateral, it's cyclic quadrilateral, and we have, so therefore, so this angle, which is equal to 90 degrees minus beta from the right triangle, this one we calculated, so it's equal to this angle 90 degrees minus beta, right? HC HBH. So let me show it. So this angle is equal to this angle. Yeah, highlighted with blue. So now similarly we have this angle is equal to this angle, and both of them, so it's also actually equal to 90 degrees minus beta, so like I can actually select it with the same color. Because from another right triangle, CHCB, from this right triangle, we calculate this angle as 90 degrees minus beta as well. So, and this is 90 degrees minus beta. And by the way, here we established again that the altitude is a bisector in the orthic triangle, which is a well-known fact and which I proved in another video. But so the point is that now we need to calculate the opposite angle in this quadrilateral, so this angle, and this is calculated, so this angle is calculated as an external in this isosceles triangle, right? So we have this angle as 90 degrees minus alpha, this is 90 degrees minus gamma. So because it's an isosceles triangle, so this is also 90 degrees minus alpha, and this is also 90 degrees minus gamma. And so now this angle is an external in this isosceles triangle, so it's equal to the sum of the two other angles. So it's equal to, there is no place here, like I will write it separately here. So the angle HC and B H, so the angle that I highlighted in green on the picture, so this is equal to 90 degrees minus alpha plus 90 degrees minus alpha, so this is equal to 180 degrees minus 2 alpha, right? And similarly the one that I highlight in yellow, so this one, So this was green, and this yellow one is a angle HA and BH. So the one that I highlighted in yellow on the picture. So this angle is equal to so it's an external angle in the triangle, and BBHA, so it's equal to the other two, to the sum of the other two angles. So 90 degrees minus gamma plus 90 degrees minus gamma, and this is equal to 100 degrees minus 2 gamma. So when we sum these two angles together, so the angle HC and BHA is calculated as the sum of these two, this one plus this one, and so it would be 180 degree minus 2 alpha plus 180 degrees minus 2 gamma. So this is 360, or it's better to write it this way. So it's equal to 2 multiplied by 180 minus alpha minus gamma. And we remember that because alpha, beta, and gamma are the angles in the original triangle, so their sum is 180. So 180 minus alpha and minus gamma, this is exactly beta. So this sum is, so this expression is equal to exactly 2 beta. Right? And so now we see, so we see the sum of the opposite, so in the quadrilateral, so the quadrilateral HC and B, HA, HB, the sum of the opposite angles. So the angle HC and B, HA that we just calculated, this one, plus the angle HC HB, HA. So this one we just calculated, this one is 2 beta, and the other one, so this one is here, so it's 90 minus beta plus 90 minus beta. So this is 180 minus 2 beta, right? So in total we have, I see that 2 beta and 2 beta cancel each other, so in total we have 180 degrees, and this proves immediately that this quadrilateral is cyclic. So therefore HC and B, HA, HB is cyclic, and so therefore NB lie on the circle omega. And so similarly the other two midpoints. So because of the symmetry, similarly NA and NC also lie on omega. So all 9 points lie on omega. So this basically concludes the proof. So I will notice that this last part, so the proof that NB lies on omega, like there is a different proof, not like without calculating angles, like using homothety, but it's kind of because homothety is kind of considered an advanced topic, so like in that sense it's more complex, but it's kind of more beautiful, I would say. And also this proof, so I will show it in the future video, but this proofs also like not only establishes that NB lies on this circle, but it also establishes where the center of this circle lie. Yeah, and for the radius, so yes, so for the radius, actually, I can say it now, that the radius of the 9-point circle is twice smaller than the radius, the radius of the circumcircle of the original triangle, and this is simply because so in the original triangle we have circumcircle, and then we have this the midpoint, because the midpoints of every side lie on this 9-point circle, and so we know that this triangle with the midpoints, it's twice smaller than the original triangle. Like it's similar and twice smaller because the this segment connecting the two midpoints is twice smaller than the opposite, than basically this side. So like this and this are equal. So this is equal to this, and this is equal to this. So this triangle is twice smaller than the original triangle, and because of that, its circumcircle must be twice smaller than the circumcircle of the original triangle. So that's how we established that the radius of the 9-point circle is half of the radius of the circumcircle of the original triangle. But where its center lies, it's a more it's more difficult to prove, and we will use homothety for that, and you can check the next video for that. So that's it for this video.